Hello, my name is Dan Paraschiv.
And Dan,
I thought, okay.
and next speaker is Dan Paraschiv from Universitat de Barcelona, who will talk about achievable connectivities of the two components for a family of rational maps. Please go ahead.
Thank you. Hello, my name is Dan Paraschiv, and it is a great honor for me to have your attention. Today, I will talk about achievable connectivities of other components for a family of rational maps. And this is a joint work with my Ph.D. supervisors, Jordi Canela and Xavier Arquer. I will skip the complex dynamics basic definitions, as I'm sure that by this point, everybody already knows them. So let me get straight to the point. First of all, what is the connectivity of Fatou component? The connectivity of of a domain on the Riemann sphere is the number of the connected component of its boundary. So of course, for a Fatou component, the connectivity is the number of boundary components. Now, by the no-wandering domains theorem, all Fatou components of rational maps are eventually periodic. That is, they eventually map onto a periodic Fatou component. Now, by the classification theorem of Fatou component, periodic Fatou components can be Sigaldics, which have connectivity 1, Hermann rings, which have connectivity 2, or basins, which can have connectivity 1 or infinity. Now, strictly pre-periodic Fatou components of rational maps can have finite connectivity greater than 2. And for any given n, there are examples of rational maps with Fatou components of connectivity n. These Fatou components can be obtained either by quasi-conformal surgery or by giving explicit families of rational maps. However, the degree of rational maps grows rapidly with n in these examples. Now, Jordi Canela has previously proven that for a family of singular perturbation of a finite Blaschke product of degree 4, there exist parameters such that the dynamical plane contains Fatou components of arbitrarily large connectivity. Now, let me introduce a few examples of perturbation maps. By adding a pole to the superattracting x.0 of z to the power of n, McMullen has obtained a family of maps, z to the power of n plus lambda over z to the power of d, such that for lambda small enough, the Julia set is a counter set of quasi-circles. Then, 15 years later, Devani, Luke, and Lubinsky have proven the so-called escape dichotomy. Since the orbits of the free critical points are symmetric in respect to rotation, depending on the location of an arbitrary critical value, we may have that the Julia set can be a counter set of quasi-circles, or a Sierpinski curve. In this image on the left, we have a counter set of quasi-circles, and on the right, we have a Sierpinski curve. A Sierpinski curve is a set which is homeomorphic to the Sierpinski carpet fractal. And it arises naturally from the iteration of z to the power of n plus lambda over z to the power of d. And finally, recall that Blaschke products are holomorphic maps which map the unit circles to itself. For the Blaschke product of the form z to the power of 3z minus a over 1 minus a bar z, Jordi Canela has proven that there exist parameters lambda such that the Julia set is a countable union of counter sets of quasi-circles and uncountably many point components. Observe that all of these unperturbed maps have the unit circle as an original Julia set. So by adding a perturbation, the dynamics become much richer. Here is such an example in the Jordi Canela family. Observe that in here, we have a triply connected Fatou component, where he has proven that lies the unique free critical point, which we will see later that also happens in the family that we present today. Now we can move on to our work. We have initially studied perturbations for z to the power of n multiplied by z minus a, which is a family studied by Pascal-Roche. After proving most results, it has become clear that we have mostly used the topological properties of the map, so we have then tried to generalize it as much as possible. To keep the perturbation map understandable, we have decided for a simple configuration the dynamical plane. More precisely, we have decided to have A such that the Julia set of the unperturbed map to be a quasi-circle, separating the bases of attractions of 0 and infinity. Let me draw. So we have the Julia set consists in one quasi-circle separating 0 and infinity. 0 is a super attracting fixed point of degree n. 0 has degree n. And since we have chosen the degree of the map to be n plus 1, there exists another free critical point inside the immediate basin of attraction of 0, which we will denote by mu 0, which iterates towards 0. Infinity is an attracting fixed point, and the basin, of course, also contains n critical points, which may also be infinity. But once again, infinity is not necessarily a super attracting fixed point. Now, let me switch to the previous one. So thinking how we could generalize these topological properties the most, we have arrived to the conclusion that the best family of maps to use is this one, z to the power of n multiplied by z minus a over q to the power of z, where q is a polynomial of degree at most n, such that our map is degree n plus 1, and infinity is a fixed point, and q of 0 is different from 0. Then we add the perturbation to our map. We obtain the map Snd lambda equal to z to the power of n multiplied by z minus a over q plus lambda over z to the power of d. We assume that the initial family satisfies the previous conditions, and we also need to assume that our map satisfies the condition 1 over n plus 1 over d is smaller than 1. I want to point out that in the original Macmullen case, this was coming from a natural inequality appearing from annuli. But in our paper, it appears as a tool in proving the result. Here is an example of our family. On the left, we have Milnor's family, that is Pascal-Roche's family for n equal to 2, for a equal to 0 plus 0.9 plus 0.6i. And on the right, we have our map after perturbation for d equal to 3 and lambda equal to 10 to the power of minus 7. Observing here another triply connected Fatou component. As we will further see, it contains once again the unique free critical point. Let's move on to specific properties of the dynamical plane of the perturbed family. Now, let modulus of lambda small enough. Then the following may happen. I'm going to once again draw because things are a lot more intuitive this way. So we have that the immediate basin of attraction of infinity maps to itself, which we denote by a lambda star of infinity, because now infinity maps to itself with degree n plus 1. So the immediate basin of attraction maps to itself with degree n plus 1. Infinity is here. and it may contain and its boundary is a quasi-circle. This is the first result that we have obtained. Because further, we will assume at some point that all critical points eventually iterate towards infinity. From this simple fact, we'll have that actually all the boundary components of the Fatou components will be quasi-circles. But now let's just stay here in the dynamical plane. So we have the immediate base which maps itself with degree n plus 1. We have its boundary, which is a quasi-circle, and separates infinity from 0. Then we have that there exists this Fatou component called the trapdoor T lambda, which usually appears while doing perturbations. This is T lambda. Okay. And T lambda maps with degree D to the immediate base of attraction of infinity. So there are no more preimages of infinity, because 0 maps with degree D and the preimages in the immediate base map with degree. There are n plus 1 of them. Now, we have that there exists one preimage of T lambda, which we will denote by A lambda because it is an annulus. And this annulus also surrounds z equal to 0. And it lies between T lambda and A star lambda of infinity. This is A lambda. And if lambda contains n plus d critical points and n plus d zeros. So A lambda maps with degree n plus d to T lambda. Of course, this leaves us one more 0, which we will further denote by W lambda. And since until now we have accounted for 2n plus 2d minus 1 critical points, there exists exactly one free critical point in this family, which is somewhere here. Call it nu lambda. Okay. And the next propositions tells us that not all, of course, the preimage of 0 must lie in the preimage of 0. Let me switch here again. So the preimage of 0, W lambda, of course, it must lie in another Fatou component because T lambda is a Fatou component, which will be denoted by D lambda. And D lambda allows outside A lambda, and of course in the interior of the region bounded by the boundary of the immediate basin of attraction. Now, let me introduce the Riemann-Hurwitz theorem. This is probably the major result that we can always apply to obtain connectivity of a set. Now, the Riemann-Hurwitz formula. Let U and V be two domains of the Riemann sphere of connectivities mu and mv, and let F from U to V be a proper map of degree D with R critical points counted with multiplicity. Then the connectivity of U minus 2 is equal to the degree of the map multiplied by the connectivity of V minus 2 plus the number of critical points. Observe that if the multiplicity of a set V is equal to 2, then if its image contains no critical point, the multiplicity of U is also 2. So the preimage of an annulus, if the preimage does not contain a critical point, the preimage will also be an annulus all the time. Now we are going to assume that the free critical point in our family lies in an eventual preimage of A lambda. Since A lambda and D lambda are the only preimages of T lambda, and all the we want to make the assumption that all the points iterate towards infinity, then the free critical point must lie either in an eventual preimage of D lambda, the disk, or A lambda, the annulus, which maps the degree m plus d to T lambda. Now, if the free critical point lies in a preimage of D lambda, we have that all Fatou components have connectivity 1 or 2. And this does not interest us. So we'll assume that the free critical point lies in a preimage, an eventual preimage of A lambda, which also surrounds it equal to 0. This will be made clear later. Now, by applying Riemann-Hurwitz, all eventual preimage of A lambdas until we eventually reach the critical point are annuli. And when we finally reach the critical point, we obtain that U nu, the Fatou component, which contains the free critical point, has to be triply connected. And it also lies outside the A lambda. Now, recall that the family that Jody Candela has studied before is perturbation of a finite Blaschke product. We have the following proposition in our case. Let S and D lambda satisfy all the necessary conditions. Let lambda of modulus small enough. Then there exists an analytic Jordan curve inside the annulus A lambda such that our map is conjugate to, is quasi-conformally conjugate to a Blaschke product on the region bounded by the immediate basin of attraction of infinity and the annulus A lambda. So all the maps in our family behave as a Blaschke product on the most interesting region. Now we can move on to the main results, the main theorems. First, let me state theorem A. Once again, let S and D lambda satisfy all the necessary conditions. Let lambda of modulus small enough, and assume that the free critical point lies in an iterate preimage of A lambda, which surrounds it equal to 0. Now let K be the minimal number of iterations needed by the free critical point nu lambda to be mapped in the region bounded by the annulus A lambda. Let U be a Fatou component of connectivity kappa. Then there exists some natural numbers ijl such that kappa is of the following form: m plus 1 to the power of I, b to the power of j, n to the power of l plus 2, and where the exponent of n is smaller or equal than the exponent of d multiplied by the number of iterations needed by the free critical point to be mapped in the region bounded by the annulus. So how do we get to this general form? Here we have a sketch of the proof. As we have discussed before, iterated preimage of D lambda have connectivity 1, iterated preimages of A lambda, except for eventual preimages of the Fatou component containing the free critical point, have connectivity 2. Now, preimages of a Fatou component which does not surround z equal to 0 map with degree 1 onto U and do not surround z equal to 0. This is a property which arises from the Blaschke conjugation and tells us that the Fatou components which do not surround z equal to 0 cannot increase the achievable connectivity while iterating backwards. Now, eventual preimages of U sub nu which surround z equal to 0 may map forward with degree d, n, or n plus 1. By the Riemann-Hurwitz formula, it is clear that since the degree can always be multiplied by dn n plus 1, we can always increase the exponents of dn n plus 1. And the +2, of course, appears from here, from this -2 from the Riemann-Hurwitz formula. Now, the condition which we have stated in here arises from the fact that the Fatou component in our family, which can only iterate backwards at most k times with degree n before having to iterate with degree d. So that inequality arises naturally. And we can iterate backwards with degree d and then +1 as many times as needed in our family. Now finally we apply Riemann-Hurwitz and we conclude the proof of the statement. Let's move on to Theorem B. While Theorem A has described the general form of all the possible achievable connectivities, Theorem B says that for any given parameter, these connectivities are certainly achieved. Let's go into details. Let S and D lambda satisfy all the necessary conditions. Let modulus of lambda small enough. Assume that the critical point lies in a pre-image which surrounds it equal to 0, and let Ks be 4. Now, for any given IJL natural numbers, such that L is smaller or equal, the exponent of N is smaller or equal than the exponent of D multiplied by K minus 1, then there exists a Fatou component U of connectivity kappa m plus 1 to the power of I, d to the power of j, and to the power of L plus 2. So this theorem says that pretty much almost all of the connectivities are achieved. And we have seen that in particular, there exists only one possible case where everything that we have described in Theorem A may not be achieved. And finally, the biggest result in our paper. Until now, we have tried to describe statements in the dynamical plane, but we have not proven in any way that they may happen. Theorem C says yes, everything that we have described in Theorem A and Theorem B always happens. Now, let S and D lambda satisfy all the necessary conditions. Then, for any IL greater or equal than 0 and J bigger than 0, there exists a parameter lambda such that our map has a Fatou component of connectivity kappa equal to n plus 1 to the power of I, d to the power of j, n to the power of L plus 2, and the Fatou component of connectivity kappa equal to n to the plus 1 to the power of I plus 2. So for any connectivity of the desired type, we have that there exists a parameter for which such that its dynamical plane contains a Fatou component of the desired connectivity. Now I want to give a sketch of the proof. It's not clear for me how much time I have left.
Around 3 minutes.
3 minutes? Okay. Then I will just say this. As an idea of the proof, as lambda approaches z equal to 0, the number of iterations required by the pericritical point to reach the area bounded by the annulus, which contains the critical points and the zeros increases. We prove that for large enough k, for such large enough number of iterations required by the pericritical points to reach the annulus, there exists a parameter such that the triply connected Fatou component is properly defined. And the conclusion follows from Theorem B. Thank you very much for your attention.